So yeah, today I'll be showing you how to use the Intel VTune Amplifier to profile your Python application. So I'm sure all of you are familiar with Python. It's gotten quite popular recently. It's awesome to quickly build up your applications. It's got a lot of libraries and a very good user base that can help you with building your application using libraries. In addition to that, it has a lot of frameworks that are actually optimized for the hardware. So even though Python is an interpreted language, if you're using one of these optimized frameworks, it can perform quite well. So I've seen three types of Python workloads. So the first one being just using Python with standard libraries, maybe using something like NumPy. And this first use case, a lot of times the libraries are not really optimized for the hardware, so the performance is not there. I think a lot of people use this use case for data processing and I/O applications or general type of scripting. And then I think most common way to use Python nowadays for HPC is to rely on frameworks such as TensorFlow, and most of the time these are actually optimized for the hardware that you're running, so they're vectorized and multi-threaded. So I think this is the main use case for people who do machine learning and AI applications. And the third use case is to rely on Python to build up the infrastructure for your application and then actually write custom libraries in C that actually do all of the heavy lifting for your application. So you can profile all of these workloads using Python. So if you haven't used profiling, essentially what profiling does is you run your application through a profiler, and it uses time sampling and hardware counters on your CPU to give you insight into the performance of your application. So for example, you can get insight into your L1, L2 cache performance. You can see any sort of NUMA penalties that you might be paying. And VTune works at many scales, so it works on a single core, single thread, multiple threads, and multiple ranks. So you can use VTune to analyze your application at any scale. The overhead for a lot of these collections is really low. So it's quite nimble, and it gives you a lot of information. And unlike a lot of profiling tools that just do text-based output, VTune has a nice graphical user interface, and which allows you to sort information in many different ways and basically turn information into insight. In the slide, I also mentioned this tool called Intel Advisor, and Intel Advisor is not necessarily a profiling tool, but it does some static and dynamic analysis to give you insight into the efficiency of your vectorization. And I'll mention this tool again a little bit later. So VTune has a lot of predefined collections. So here's a pretty extensive list, and you can actually run almost any of these collections on your Python application. But the ones highlighted in light blue, we have Python support for. So what that actually means is that if you use the light blue ones on your Python application, you'll be able to get native Python call stacks. Whereas if you do something like general exploration, your Python layer will be grouped into this kind of a monolith. So most of the time when I'm profiling a code, I use either HPC performance or general expiration. And that's because general expiration focuses a lot on the core level, and HPC performance is better suited for multi-threaded workloads. And these analyses actually are a superset of these smaller analyses, such as basic hotspots. So since the overheads are so low, most of the time I see no reason not to use one of these aggregate analyses. And I'll show you how to use both of them later. So if you're trying to get started with VTune, for example, if you're a Theta user, you'll find the VTune installation under soft compilers, and there is this amplexc vars shell script, and if you source that, it will set up the path and everything you need to get started with VTune Amplifier. Otherwise, if your cluster has modules set up, you can use those, or you can export all the variables yourself. So the syntax for using Amplifier is pretty simple. It's just action followed by action options, and then you do a double dash, and after that you just run your application as you would normally. So the simplest use case for hotspots is just -c, which is short for collect, and then hotspots -- and your Python interpreter and the Python script. So if you're new to VTune, there's the -h, the help option. So if you do -h collect, it will list actually this list of predefined collections that you can run. And then you can string that with -h collect hotspots, and that will give you additional information into all the different knobs that you can tune to customize your hotspot analysis. There is, I recommend bookmarking this link at the bottom. This is the command line reference for VTune. I use this basically every day. It's got a nice search function and a lot of examples that you can refer to if you haven't used a particular analysis before. So I have a simple example here on the right. Just does some math, and on the left is an example of how you would run that. So you're going to do amplexc and collect hotspots on this Python application. And once the collection is complete, you can open the GUI and view the results. So once you open the GUI, you're going to be dropped into this summary window. And there's quite a bit of information here. So first, you have your elapsed time for the application and on how many threads it ran. You have your top hotspots, and these can be either functions or loops. You have a histogram of your average CPU usage and some information about the platform and the type of analysis that was collected. Now at the top, you have three different views. You have the bottom-up view, the Callee view, and the top-down tree. So quick plug here. I ran an example using Anaconda distribution for Python, and here we have a runtime of 24 seconds. And Intel actually has a distribution for Python as well, and much like Anaconda, it comes with a lot of libraries already pre-packaged, but these libraries are actually built against MKL, so they're already multi-threaded and they're optimized for performance. So you see that I didn't really change anything besides my interpreter, and my runtime is about 3 times faster, and I'm using multiple threads. So going back to the bottom-up view, this is the basic kind of hotspots view where I start a lot of times. Here you see a list of either functions or loops. You have options for grouping your information, your data in different ways. You have this change viewpoint button. So if you remember when I said that, for example, general exploration is a superset of other analyses. Once you collect general exploration, for example, it will also have all the information necessary to view basic hotspots. So you can change between these analyses easily without having to rerun your collection. Now, if you click on one of these triangles, this will drop down a menu, and it will show all the functions that are calling this particular function. And if you keep clicking, you can essentially go all the way to your main. In addition to this, you can also filter in or out by selection. So, for example, if you extract a kernel from your application and you have to do some sort of a setup just to get it running, that setup might not be necessarily indicative of your standard run. So you might want to just completely exclude all of the setup functionality. So you can do that here. We have all of the filter options at the bottom here, so you can select which process you want to look at or which thread. If you want to look at a particular module, you can do that. A very useful one is in the bottom right, the functions only. You can change your view to see either functions, loops, or both. So a lot of times, if you're exploring things to optimize, loops, for example, are oftentimes your vectorization targets. So you can just look at the loops. And we have the clear filter button over here. So a nice, going back into the grouping view, a nice option for Python is this module function call stack. And that is because in the performant Python workloads, a lot of time is being spent in outside libraries. So you might want to group by that. Another good one is the thread function call stack. That's useful if you're trying to see if there's any performance difference between your threads. So if you go into that, you'll see that now information is grouped by first the module, and then if you're going to click that module, you'll see all the functions that fall under that, and then you can keep going down the call stack. Now we have the top-down view, and this view is particularly useful if you're trying to understand the exact distribution of the time where you're spending it inside your code. So you're actually able to click at any of these levels, and if you double click on that, it will open the source viewer, and you see this is the source that I ran, and it shows me the percentage of time, the percentage of overall time that I'm spending line by line. So that gives you quite a bit of insight of where you might want to spend your time optimizing. Now this last view is the Callee view, and it's kind of a mix between the two previous ones. This one's more useful if you have a particular function that you're interested in and it's being called in many different places, and you don't want to go to top down or bottom up and keep tracking that. If you run the memory consumption analysis, you'll get a list of modules and data structures and their associated sizes, as well as a timeline of your allocations and deallocations, so you can get some insight into your memory footprint throughout your runtime. So VTune is also able to profile MPI jobs as well. Here's a link to Git repository where I pulled an example from. and I use that. So there's two options that you have for profiling MPI workloads. So one is to collect information on every rank. That's useful when you might have some sort of a load imbalance, or different things happening on different ranks. So if you know that you don't have any load imbalance and the load across all of the ranks is pretty much the same, you're better off collecting information only on a select rank. Another issue with that might be that you might not have enough VTune licenses to collect on every rank. So if your system uses MPI, all you do essentially is just do prepend MPI run to the previous command that we did for VTune. And if you want to profile only select ranks, MPI run has this SPMD notation where you just do MPI run -n, some number of ranks, followed by all the options. And at the end of that, you just do a colon, and then you can select another set of MPI ranks and launch either a different binary or a binary with different options. So in this case, we ran 2 ranks, one with VTune and one without. Now, if you are a Cray user, it's slightly different because Cray systems use AP run, and AP run actually does have the SPMD notation like MPI run, but the difference is that that AP run has a limitation that if you want to use the SPMD notation, you have to use at least 2 nodes. And a lot of times when I'm profiling MPI workloads, I'll be spawning MPI ranks on a single node, so that's not really an option. So I have this script that I keep in my home, and you essentially launch this script through AP run, and as soon as you do that, AP run will export your this environment variable alps app PE, and then it's essentially if you're rank 0, you're going to do one thing, otherwise you're going to do something else. So an example here is I do AP run -n2, and I run this profile 1 shell script, and then I just pass my Ample's XCCL line along with my Python application. So one node is going to be launched with VTune and one is going to be launched without. Once that completes, you can go back into your bottom-up view, for example, and now you see a timeline. So each individual rank and thread are displayed in the bottom left. So your MPI ranks are going to be labeled as OMP master thread number 0, followed by any number of threads that each rank is using. So in this case, you can't see the other thread 0, but yeah, so let's see. So the third kind of Python workload is the one where you're using your custom built libraries written in C. And if you're trying to optimize those, you don't have to build up a main in C. You can actually still launch your application through Python. So there's a link to GitHub for this quantum chemistry package that does exactly that. And there's not a whole lot of prerequisites really. You just have to make sure that the external libraries that you're using, that they're built with -G option, and that is just to include the debug symbols. In addition to that, you might have to tell VTune where to find the sources if you want to click on things and then the text editor show up and see some information line by line. If you don't do this, it might not find it automatically, and you might have to link to the source through the dialog box that pops up. So for profiling external libraries, it's essentially a two-step process. So first, we're going to run the basic hotspots analysis, and that's essentially to get a good Python call stack and figure out kind of the structure of the code and where the overall time is being spent within each layer of Python. And after that, we can do, so my two favorite ones are general exploration, which is good for microarchitecture, and HPC performance, which is a little bit more useful for threading. So I ran this example first using hotspots, and you can see all the different Python layers and calls, and you can click on each individual layer, and you're going to be dropped into your Python source file, and you'll see the percentage of time being spent on each line. So this gives me a better general understanding of my Python application. And then I run the general exploration. So once you run this, now you can actually go in and see some additional lower level performance information of the library that you're trying to profile. So you'll see stuff like percentage front end bound, percentage back end bound, clock ticks, and the CPI rates. So if you're trying to do some low level optimizations, you can then go into your source, modify, recompile, and rerun. And then, like I mentioned at the beginning of the presentation, we have also this advisor tool. So if you're really trying to get performance out of your application, you have to make sure that it's vectorized. And advisor is a great tool for that. As you can see here, it shows me which loops were vectorized. It will tell me some of the performance issues that I might have. It will tell me the instruction set used and the vector length. And for the workloads that are for functions or loops that are not vectorized, it will give me suggestions, and it also has different set of analyses that you can run after that. So for example, you can run the advisor dependency analysis, and what that will do, it will look at all of these loops that were not vectorized, and it will check for dependencies, and it will tell you if it's actually safe to force vectorization or not. And it also has this source viewer where you can see the cost of each individual line, along with any kind of things to notice in regards to your performance. So if, for example, your Python application runs very quickly, it might be the case that VTune does not get enough samples to display information. So it might be the case that it's not practical for you to increase the runtime of your application. So in that case, you can increase the sampling frequency. If you're running an application that uses a lot of threads, VTune will generate a lot of information, and this information can take actually a really long time to finalize, especially on a platform like KNL, because finalization is a single thread process, so it might take a long time. So in that case, you might want to set your finalization mode to none, and then copy the results over to a system like Skylake and finalize there. Now, if you see some unknowns in your application, you should go back and check that everything was compiled with -G, and like I mentioned earlier, you might want to include your search directories for the sources, and you can do this either at the collection step or at the finalization step if you're using command line to finalize, or alternatively, you can click things around in the GUI to get all all the sources linked there. So, questions? Get any text questions, right?
I'm not seeing anything in the chat yet.
Cool.
I have a question.
Sure.
So thank you, this is helpful. So if I were to do the general exploration, does it still come back with the full call stack of information?
No,
even
not for Python.
hotspots, like I'd have to run hotspots to get the
Yeah,
call
because the basic hotspots uses sampling, whereas general exploration will collect hardware counter information. So yeah, you're not going to be able to get your native Python call stack using general exploration. So that's
Okay.
why I run both, yeah.
Okay, yeah, thank you.
So this is your opportunity to ask Paulius about everything that you've had trouble with the first time you tried this.
It looks like a chat question came up actually.
So the chat question is, I have a specific question about the HDF5 library. I'm trying to use the Python binding H5 to get good read-write performance along multiple axes for a data set of size 40K by 40K by 100 of float 32s. Does VTune give the total number of I/O calls a single line in Python makes? I'm not sure I parsed the question. The part about the single line in Python makes.
So there is an I/O analysis that you can run, but that is not one of the basic ones that we support Python call stacks for. So I'm not sure. I have not analyzed I/O performance for a Python application, but you'll be able to. Ultimately, it's supposed to be calling. Some sort of a SO, right, for performance. So you might be able to get that information using the I/O performance analysis.
Okay, he says, for example, a line that says dataset write from NumPy to an HDF5 file will make multiple I/O calls depending on the chunk size and cache size. So he means the underlying I/O calls. So is there any way to get a count of those calls?
You'll be able to get a count of those calls. Yeah, I think you'll be able to get a count of those calls, but I'm not sure if you're going to be able to associate it with a particular line. So it's all going to be aggregated under the library that you're using to do the calls.
So you can't get a breakdown of
line by line,
the call tree below that line.
I don't think so.
Just in general.
No. You might be able to figure that out using, both the hotspots and then doing the I/O analysis. But since I haven't profiled an I/O workload, I'm not exactly sure on that.
Okay, we possibly, for the future, might want to have an I/O centric talk to, after we have some time to dig into some of those issues. Does anyone have an early experience with trying to use VTune with Python that they learned something to do or not to do that they'd like to share with the rest of us?
Hi again.
Mhm.
Okay, so I'm at NERSC and I do a lot of stuff on KNL, and I've had a lot of trouble trying to finalize. I was hoping that I could say finalize equal none and then finalize on our Haswell nodes because it's faster. But when I did that, I lost all my call stack information. Um, so even when I was, saying source directory, I found that I didn't have the info unless I actually finalized on the KNL node, which took like 8 hours.
All right. Well, that's quite unfortunate. I'm sorry to hear that.
Is that
Um,
common, or I mean, should it work?
I've
Is
run
it
into
my?
that. I've run into that. And if you are, did you specify the source as well as the binary?
Yeah, I think so.
All right. Well, if you specify both the source and the binary, then it might be a bug, but I can't tell you exactly. I mean, it should it should finalize properly. We're using the GUI to finalize or the command line?
Command line.
Command line. Um, yeah, might be a bug. I'm not sure. I've run into a similar issue, but it's not very common for me for sure.
Okay, thank you.
Oh, so we have a follow-up comment about the I/O, the previous I/O question. Uh, he says, I ask because there's a number of variables to be set for such a task, including but not limited to chunk size, caching policy, number of chunk slots in the cache hash table, compression filters, etc., and one needs a tool to help setting the values for these. So if I guess I could extend that question and ask if VTune is not the right tool, do you know of a better one to address that?
In the context of Python, no, I'm not sure about that. So especially if you need to associate all of those calls with a particular line or call, then that might be difficult. But for the overall performance, yeah, I think the I/O analysis would give you that. It comes with for C, yeah, the I/O performance analysis collection would be useful for that. Gives you it gives you a timeline. It gives you a timeline and it will display the bandwidths that you're achieving. And then I'm not sure if it's going to be exactly straightforward and give you the answer to what you need to set your chunk sizes to, but you can experiment and then see the changes in your performance. So, and you might be able to do this for through Python as well.